Hello everyone, welcome to my presentation. My name is Tingyi Zhou. I'm a recent Ph.D. graduate from Jalali-Lab at UCLA. I've been working on the symbiosis of physical system and AI algorithm for the past few years. Today, I would like to talk about one of our recent work, real-time computing with femtosecond laser pulses. In this work, we propose an ultra-fast computing technique for improving femtosecond instrument. The main drive behind is the importance of instrumentation in scientific discovery. A great example is Galileo's telescope. So in 1609, Galileo improved the telescope, which allowed people to observe and collect data of the trajectory of celestial body. Later on, theorists like Newton used that data to develop the theory of gravitation, which becomes a major part of the mathematical principles of natural philosophy. All of this cannot happen without the invention of new instruments. In other words, new instrument leads to new science. The scientific research today require even more advanced instruments. Specifically, many of them focuses on events that happens in sub-picosecond timescale. This requires instrument that works fast enough to capture these events. One powerful tool is the femtosecond laser pulse because first of all, it is the same timescale at the ultrafast events, so it can act as a probe. More importantly, it has a broad spectrum with all kinds of colors or wavelengths, which gives us a lot of room to work in. We can exploit this domain by encode lots of information onto this broad spectrum and then use linear or nonlinear optics to manipulate this information. For the linear optics, we can use them to read the information out in real time. This is known as the photonic time stretch. For nonlinear optics, we can use them to process the information for real-time computing in ultrafast instruments. This is again a good fit for photonic time stretch. So first, please allow me to introduce the photonic time stretch. The photonic time stretch is a technology that can perform measurements of ultrafast signal at billions of frames per second. It works under the theory of dispersive Fourier transform, where the chromatic dispersion in an optical media such as an optical fiber, maps the spectrum of an optical pulse to a temporal waveform whose intensity mimics the spectrum. With dispersion, the waveform can be very wide, basically a stretched version of the spectrum. If the information is encoded on the spectrum beforehand, it can also be slowed down during this process. This technology was initially developed in 1998. It helped the first discovery of the optical rogue waves and the real-time observation of the birth of mode locking. Also, it initiated one of the world's fastest camera. People also discovered some other applications in recent years, such as observing relativistic electron dynamics, spectroscopy for combustion, observing shock wave, build up a gyroscope, and also the spectroscopy of chemical bonds. One major application, which is also related to the topic today, is the time stretch microscope. Here is a short video on time stretch microscope for cancer diagnosis. In this system, the femtosecond laser pulses are spatially dispersed through a pair of diffractive gratings, becoming rainbows, so that each wavelength, or we say color, corresponds to a spatial coordinate. The rainbow is then focused onto a microfluidic channel and illuminate the cells passing by. As we can see, if we zoom in, there are two types of cells. The white one is a normal white blood cell, and the yellow one is the cancer cell. We can see here, each rainbow flash on one line of the cell, and this encodes the spatial feature of that line onto the rainbow, which is basically the spectrum of the femtosecond laser pulse. There is a reflector on the back of a microfluidic channel so that the encoded pulse can be reflected, travels back into an optical circulator, which redirect the pulse to a dispersive fiber. In this fiber, the dispersion stretches the pulse so that its temporal waveform mimics the spectrum. The stretched pulse is then detected by a photodetector, digitized by an analog to digital converter, and sent into a digital computer, in this case an FPGA. In the FPGA, the acquired 1D scans are reshaped to 2D images and then classified. This ultra-fast imaging system generates terabits per second of data. This is good for machine learning algorithms, especially deep neural networks, because they require large datasets for training. However, there's a big problem. On one hand, ultrafast optical instruments like the time-stretch camera we just shown can capture billion frames of data per second. On the other hand, in order to achieve sufficient accuracy, the neural nets need to be complex enough, which leads to milliseconds or tens of milliseconds inference latency. Essentially, there's a huge mismatch between the timescale of neural nets and the ultrafast optical instruments. And even if we can run neural nets at that rate, billions of inferences per second will have prohibitively large power dissipation, making it impossible. To solve this problem, we proposed the Nonlinear Schrodinger Kernel. This is published earlier last year on the Journal of Lightwave Technology. Here we call it kernel because our technique shares some similarities with the numerical kernel trick in machine learning. The kernel trick is a common method used in machine learning. It works by processing the input data with a nonlinear kernel function and then send results to a light machine learning model. Let's look at this example. Here we have two types of data, the red square and the green dot. We cannot use a linear classifier because the boundary of the two classes is highly nonlinear. A simple workaround is to use the linear function, or we say kernel, to project the data into a new space where the classification can be achieved using a simple linear classifier. And with a similar idea, our kernel also performs a nonlinear projection. Here is an illustration of the nonlinear Schrodinger kernel. This technology uses nonlinear Curl effect in the optical component, which reshapes the spectrum of a femtosecond laser pulse, performing complex transformation. In the start, we map the input data shown here as 1D vector onto the spectrum of a femtosecond laser pulse, with each entry assigned to a virtual input node. This rainbow is basically the femtosecond laser I've been talking about. The laser is then sent into a nonlinear optical element, where the complex nonlinear process governed by the nonlinear Schrodinger equation transforms the input data along with the optical spectrum. The transformed data is collected by a spectrometer with the same sampling dimension as the input data, and each sampling point can be viewed as a virtual output node. The collected data is then sent to a lightweight digital linear classifier. In this system, the heavy lifting part of the computing is done in physical system. Through this process, the nonlinear transformation projects the data onto a new space. In this space, the previously linearly non-separable data becomes linearly separable. This way, we can use a linear classifier with low computational complexity for nonlinear tasks. However, I want to emphasize that our kernel is not any form of instantiation of the existing numerical kernel function. It came purely from the physical systems. Here's an actual experimental system. It starts with the continuum femtosecond laser source. In this experiment, the mapping of input data onto the femtosecond laser spectrum is achieved by a spectrum modulator. The nonlinear optical element, which is in this case is a highly nonlinear fiber, performs the complex transformation on the input data as shown here. After this transformation, the data is captured by a spectrometer. It can either be a traditional grating-based spectrometer or a time-stretch spectrometer mentioned earlier. The captured data is sent into a digital classifier. We verified this technique against various datasets, and here we focus on the application in time-stretch microscope. Here we demonstrate the results collected using two different spectrometers mentioned in the last slides. The baseline is a pure linear classifier, and we compare the performance of our kernel with the traditional numerical kernel called the radial basis function, we'll say RBF. It shows that the nonlinear Schrodinger kernel outperforms the baseline, getting similar results as a numerical RBF kernel. Well, of course, it might not be very impressive if we only look at the accuracy. But as I mentioned earlier, the processing speed, or we say inference latency, is much more important. From our measurement, the nonlinear Schrodinger kernel has a similar latency as the linear classifier, which is 2 orders of magnitude lower than the RBF. This is already impressive, but what makes it more promising is that it can potentially be accelerated by another few orders of magnitude. In fact, from our estimation, if we replace the nonlinear fiber with an integrated waveguide and implement the linear classifier on an FPGA, the latency can be reduced by nearly 6 orders of magnitude. closing the gap I mentioned earlier. Up to this point, we have shown that our optical kernel provides enhanced classification accuracy with low latency. However, this system is open-loop, meaning there's no optimization on the results. This is because most of the components in the system are fixed with no tunability. So in the next step, we focus on optimizing our kernel. Essentially, we want to find a way to engineer the nonlinearity in the kernel. The major nonlinear effect in the system is the cell phase modulation, which is coherent. In other words, the nonlinear process is phase-sensitive. The result of the transformation is highly dependent on the initial phase of the input laser. Exploiting this feature, we came up with a tuning technique. Basically, we add a digitally generated optical phase pattern to engineer the optical nonlinearity. We call this technique phase-encoding, and subsequently, we call the phase pattern phase-code. With this phase encoding, we can then optimize the performance of the kernel using a closed-loop system. The updated system has two parts, the tunable nonlinear Schrodinger kernel and the digital feedback loop. The tunable kernel is basically the same as the previous one, a supercontinuum laser, spectral modulator, nonlinear optical element, and spectrometer. The only difference is during spectral modulation, when the data is amplitude modulated onto the spectrum, a code is phase modulated on it as well. In the digital feedback loop, the system performed classification, calculated the error, and used a genetic algorithm to generate a new phase code for minimizing this classification error. The optimization results shows further reduction in the classification error, which means that this approach is very effective. So in conclusion, our kernel can enhance the classification, and it also has a low inference latency. More importantly, we achieved optimization using a phase encoding with digital feedback loop. This provides a general framework for adapting this physical computer to various applications. Finally, one thing I have to emphasize is that the performance of this technique is still data dependent because after all, it is a statistical approach, just like all AI techniques. This is the end of my presentation, and thanks for watching.